Hey, thanks for joining us at Event-Driven Architecture with Kafka, Quarkus, and Kubernetes. So, your presenters today, I'm Jeremy Davis. I'm a chief architect at Red Hat, specializing in app dev solutions. I'm based in Atlanta, but I wish I was in Orlando with this conference in person today. I enjoyed last year's event. Maybe next year we'll be back in Orlando. And Tosin?
And I'm Tosin Akinosho. I'm an Openshift Solutions Architect Specialist, and I'm based out of Atlanta as well. And I really wish that I was in Orlando as well.
All right, so our application is based around, or our presentation is based around the Quarkus Coffee Shop, which is an event-driven application that we built using Kafka, Quarkus, and Kubernetes. And we thought that the best way to introduce you to the application would be to start off with a brief demo of the app in progress. And so we will take a look at the actual application to level set for everything else that we'll be looking at. So let's jump over here to our running application. This is the Quarkus Coffee Shop. Like most coffee shops, we have a number of different drinks, a number of different things from the bakery. We have a little order board that will tell you where when your drink has been placed and when your order is ready so that you can come pick it up. We also have some other information about the Quarkus team and Twitter feed from Quarkus too. So let's order something here. Tosin, black coffee for you?
Yeah, I'll take that.
All right, so we'll add Tosin black coffee. I'll take a coffee with room. I'm going to put cream in my coffee this morning. Add that in, and then we'll place our order. So if we come down here to our order status board here, you see that our coffees are in progress and they've just been prepared by our barista, who has a funny name because our barista is conveniently named for the Kubernetes pod on which the barista is executing, right? And it disappears after a few seconds to mirror us actually walking up to the counter and collecting our drinks. Now, behind the scenes, what's going on here? We're running a number of different Quarkus-based microservices. In fact, this is running on Openshift in the cloud on AWS. I believe we've got this infrastructure stood up. I'm also running the entire application on my laptop while I'm giving this presentation. Quarkus has a really tiny footprint. So the web UI is one microservice. When we place our order, it marshals the order into JSON and pushes it onto a Kafka topic, right? So it's then going to be picked up by our core microservice. The core microservice is going to grab that order and then produce a couple of events. And events are things that our system cares about, things that are important to our business, the business of running our coffee shop, right? We just ordered two coffees, right? So 2 drinks. So what it's going to do is it's going to create 2 beverage in events, and it's going to send those to our barista microservice. The barista microservice is going to apply some business logic, and realistically, all it's going to do is just wait a period of time based on what we ordered. But it's going to apply some business logic, and then it's going to produce its own event, which is going to be an order up event. The core is then going to see that event and react to it by updating the website, and that's the workflow that we just saw happen there. The reason we've built this out using events and the reason we're using Kafka to do this are things that we will dive into here as we go through this presentation. So, first things first, why do you care about event-driven architecture and why do you care about Kafka, Quarkus, and Kubernetes? Well, event-driven architectures are loosely coupled by their nature because it's a number of different pieces or a number of different applications or services reacting to events. Because it's loosely coupled, it means that it's easy to extend, it's easy to scale up individual pieces of that. Like one of the big advantages of a microservices architecture is you can scale each individual piece. As you noticed in that demo, we had our barista was named after that particular pod. Well, if our load gets too big, we can simply scale up those pods, and it becomes very easy to have more baristas grab part of the workload, right? And it means we can push out beverages faster by scaling up. It becomes very easy to do that with a microservices architecture. And being event-driven means it's very easy for us to add classes around barista or add classes around bakery, or if we wanted to add in dry goods, right, so that you could buy T-shirts and mugs, we could add a dry goods service in as well. Now, Kafka, as you'll see, also fits into this really nicely. And when you're talking about microservices and a lot of moving parts, Kubernetes makes things a lot easier, and Openshift in particular makes this a lot easier for a number of different ways. So let's start off by looking at why we want to use Kafka, or AMQ streams as we call it at Red Hat. And Tosin, I'll turn it over to you to talk about why we use Apache Kafka in this app.
Yes, so why would we use Apache Kafka? Like Jeremy said, Apache Kafka, we call Apache Kafka AMQ streams at Red Hat. And Apache Kafka is a distributed streaming platform, and it's made just for streaming events. And let me show you why. And in traditional databases, in the next slide, in traditional databases, they normally update the same row. So let's take the orders event, or let's take this orders as an example. An order, once an order has been placed, it updates that row. And once the order is in progress, it updates that same row. And it's the same for completed and refunded. And what happens, or what you notice happen, is the row was updated multiple times. And this doesn't match very well with events. On the next slide, if we look at how Apache Kafka works in the architecture, Apache works based off something called topics and events. So we have a producer. That same order would come in through the producer, and then the order would be transitioned to the broker, and then the consumer would take that and do something with it. Apache Kafka is built for a high streaming performance and data pipelines. As we see in this next slide, Apache Kafka essentially works on the append-only log file. The good thing about this is really fast, and it can store multiple records for the same key value. So we're looking at order 123 and order 123. Once an event comes in for that order, 123 and 123, we can match those events using in Kafka based off that topic. And in event sourcing, on the next slide, GitHub works basically in the same way. So when we make a commit to our code in GitHub, it's not only storing that particular barista.json, Java file, but it's storing the whole state of your of the code that you're writing in. And with that state, it's committing each event. So you can recreate that state of the event in your repo at any time. So now we'll talk about why Quarkus.
All right, so fundamentally, Quarkus is really small, it's really fast and productive. It's also a lot of fun to use. When our developers were working on Quarkus, one of the key phrases they used was developer joy. They wanted this to be a really fun thing to program with. The APIs are very familiar, so it's not a big learning curve. It's just a lot faster and a lot smaller than what you're used to. But the best way to show that off is to do a demo. So we're going to cut over again, and now we'll look at a terminal, a real demo, not just some web pages in action. All right, so the reason I like using Quarkus is it's really fast, really small, super easy to use and get started with. So we're going to really quickly go to code.quarkus.io, and we're going to create an application. So we'll say Red Hat demos Quarkus coffee shop, and our artifact is going to be Quarkus coffee shop J4K. We use Maven as our build tool, and we're going to select some technologies. So we've got JAX-RS there. We need JSON-B. We're going to use Hibernate ORM with Panache. We're going to use Postgres. We're going to use reactive messaging Kafka, because we're going to talk to Kafka eventually. We're going to use reactive messaging. We could just grab the Kafka client, but we use reactive messaging. I think this is a nicer API. And then I need one other thing. I need JSON-P. There we go. I need JSON-P. All right, because we're going to be parsing some JSON. So we'll generate our application, and I'm going to push this directly to GitHub. So we're doing our supersonic subatomic push to GitHub. Now, git clone. Let's check my repositories at GitHub. Let's refresh that screen. Conveniently, I have GitHub waiting. There's our Quarkus Coffee Shop J4K app. Now, I'm going to put this in a directory, a print working directory. I'm in demos. There's nothing in this directory, so let's clone that project. And let's cd into the Quarkus Coffee Shop. Now, I'm going to import a new project into IntelliJ, which is my favorite IDE. And we'll say J4K demo. I already got it. There we go. J4K demos. It is a Maven project indeed. We'll open it in a new window. All right, so IntelliJ is doing its thing, importing the project. Taking a bit of time to import the project there. So what we've got here, pretty simple bare bones project. We have an example REST endpoint called hello. There's also an example web page and a test for that endpoint. So we'll take a look at both of those. Now, I mentioned that Quarkus is really small and easy to work with. And so I'm building a new microservice for my application. I also have Quarkus running in development mode. All of my microservices running locally. So I'm running my website here. I'm running my core microservice here, my barista kitchen. I've got Docker Compose running with MongoDB and Postgres and Kafka and Zookeeper. So I have a bunch of stuff running on my system, and I'm also running video recording software. So the footprint here is really, really tiny and easy to use. But because I've got these other things on my system, I'm going to come to our application properties. And IntelliJ has nice code completion. So I'm already running the website on 8080, so I'm going to run on port 8088. So let's say I'm going to start my application clean. I'm going to compile, and I'm going to say Quarkus dev. I'm also going to give it one other parameter. I'm going to say debug is 5009. So I'm going to tell it to the JDK to listen, JVM, to listen on a different port for debugging. That way I can attach my IntelliJ debugger to any of the microservices that I have running. All right, so it looks like we are now up and running. Let's go to localhost 8088. So we've got our default Quarkus page, and then we have our hello endpoint, right? So probably can't see that. So our endpoint says hello. So I said Quarkus was really nice and fast, easy to use. Let's go over to our example resource and change this. Let's say hello hello J4K. See if that looks better. That looks a little bit better. Maybe we should be a little more formal. Let's capitalize our H, right? So let's come take a look at that. Hello J4K. Yeah, that looks pretty good. Let's say that we want to parameterize that though. So we don't want to make that. We want to change that. So we'll say config property name equals. Call it greeting. That's a pretty logical name for that, right? And let's say string greeting. And now let's enter our hard-coded value there. Save that. Where's our application properties file? Let's add our greeting in there. Greeting equals hello, day 1 of J4K. See how that looks. All right, looks really good. All right, so software, writing software anyway, coding is mostly about trial and error. So closing this feedback loop or making that feedback loop as fast as possible or as quick as possible is a big win. This is pretty fast, right? If you're a Java guy, that's a pretty fast way to develop. If you're a JavaScript guy, if you do mostly Node, right, or front end work, that's pretty. You're used to this kind of feedback loop. For Java people, though, this is pretty fast and pretty nice. I also mentioned that we have a test resource here, so we can run our test right here in our IDE, or we can run it in Maven. Assuming my IDE doesn't hang, you can run it with your IDE. So we'll run our test hello endpoint, which of course is going to fail now, right? Because it's expecting hello, which is what was generated by the app. We're not going to have that anymore. We're going to fail our test. Let's make sure it fails. Remember, this piece of advice I read once was always make sure you test right, because if we pass now, we get then the wrong output. So yep, we failed. So what we're going to do here is go back here. And we're going to say test greeting equals hello. So we can parameterize our properties files. By default, tests are going to run in the test greeting, and dev is going to run in the dev. You don't have to annotate anything with prod. You can also define those yourself. Another kind of nice thing here is I'm running my application on 8088. I also have an application running on 8080. By default, the test is going to spin up Quarkus on a different port. And this annotation here, this Quarkus test, what this means is this is spinning up Quarkus, right? So it's actually booting the entire environment, and we have access. So now we passed our test, right? We have hello. We've passed our test not just because we don't just have access to a running Quarkus. We have access to anything inside of Quarkus environment. So let's call this string expected reading. So now we can test the parameters here as well, right? So we have access to those same kind of parameters. Anything that exists inside of the Quarkus space, we're going to have access here, which means beans we can inject into these tests, so we can do unit tests on things that would normally require integration. All right, so there we go. Now, later on, a few slides from now, we will come back and integrate this into the rest of our application.
So now we're going to talk about why Openshift, or basically why Kubernetes. So Openshift is Red Hat's name for Kubernetes, and what we do at Red Hat is we add some more features to make it easier for developers to develop an application. The Quarkus application is built with many moving parts, and what I mean by many moving parts is the Quarkus application is basically a microservice that consists of 5 different microservice applications, and also those 5 different microservice applications interact with a Kafka instance and a MongoDB instance, and we have to figure out how do we go and manage all those in our cluster. So that's where Openshift comes into play, and something we'll talk about later on is operators. But in this slide, you see an example of the AMQ streams operator, and it just gives you an easier way to deploy your Kafka application. So let's go into a demo and see what Kubernetes job can come out of this. How this application was set up in this cluster. So now I'm going to dig into how it looks within Openshift. So here we have the Strimzy application. The Strimzy contains Kafka, Zookeeper, and the operator, which we'll touch on a little later. But for right now, we're just going to touch on the actual Kafka deployment. So the Kafka deployment is made up of 5 different microservices, as you can see here. What I'm going to do is I'm going to show an example of scaling up and scaling down the Quarkus Cafe customer marker. The customer marker is a microservice that we have that emulates ingestion of different orders and events. So as I click on this button here, it's going to scale up the Kafka instances for the customer marker instances. And if you see under resources now, we have the customer marker running. When I click on view logs, you'll see that these events have already been created. One thing this customer marker also has is environment variables. This environment variable is defining the endpoint that the customer marker is pushing events to. So as we go back to the administrator, to the developer role here, we're going to scale this down. So as I scale it down, we'll click on this, and now that customer marker application is scaled down.
All right, so how do you try this at work, or how do you actually build an event-driven system? All right, so in event-driven architecture, you typically have one or more event producers, you have one or more event consumers, and you have something that orchestrates those events. So in our case, in the example that we saw earlier, right, the website, the UI, you enter your order, and it produces an event. It actually produces a command. We'll jump into that a little bit later. That command gets sent to our core system, and the core system then creates the necessary events, an order in event, barista in, and 2 barista in events, because we ordered 2 coffees. Those events get picked up by the other microservices, the barista or kitchen microservice, which applies some logic, does some processing, and then publishes more events. In our case, in our system, it produces an order up event, which signifies that an order is ready in the system. The core then grabs that and updates the website. It's also storing them in a database. So the core orchestrator handles all these kind of pieces, right? It puts stuff in the database, so it stores the pieces that we need of the system that we need to store, the events, and then it updates the various pieces, and it also handles creation of orders. Now, where do events come from, right? Events are at the heart of our system, but how do you determine what your events are? And what we're going to recommend you do is that you grab this book called Event Storming by Alberto Brandolini. He also has some really good videos on YouTube from other conferences that he's presented at. Fantastic material. Now, this is about group learning and group understanding of your business through the use of focusing on the events that are important to your business. The practice takes a lot of space and a lot of sticky notes. This is Red Hat's London office. That's the Thames outside of the window there. And that's about 20 feet of wall space from an actual exercise. In fact, you can see the word order on there, right? So this is how orders move through a customer's actual system. Now, these cards all have, or the colors of these cards all have a purpose. The gold or the orange domain events are the key things that we're looking at. Other things are pretty obvious, like users or a view, right? I mentioned the command is what sends an order in because a command tells the system to do something. That's not really of business importance, right? It's the event itself. It's that an order is placed or that an order is ready. Those are the things that our business cares about. These other kind of pieces we'll talk about a little bit more in depth, including things like aggregates and value objects and some other pieces a bit later. Now, this is an example of an event storm that we did. We used Google's tool Jamboard. There's lots of different kind of tools you can use. The colors didn't match up exactly, and don't get wrapped around the axle too much about your colors being perfect, but you do want to be consistent, right? Because you do want somebody to be able to look at your various event storms and make sense of them. But if you look at what we did earlier, right, our website was the user, or the user on the website creates an order in command. That is then processed by an order. That order is persisted. It creates events, right? It creates an order in event, and it created two barista order in events. The barista picked up that order in event, or it reacted to that, and it reacted that by making a beverage. And then it created an order up event. And then that gets reacted on by the core piece of the system in another part of the event storm. Right, but this is how we capture these events, and these are the things that our system needs to know about. It wants to know that an order came in. It wants to know what's in that order, right? It wants to know when that barista item is made. Those events are important because we want to, say, track the performance of various baristas. We want to know how fast we can make drinks, and that way we can staff more efficiently, right? Maybe we can promote people for being faster or for spilling less drinks, right? So those are things that our system wants to be able to capture. They're of business importance. But then how do you develop software from this, right? How do we turn these events into an actual software system? So more books to read, right? So more of a reading list. You may not have known you were going to get a reading list or summer reading list by attending this talk. So Domain-Driven Design by Eric Evans is a fantastic book. It ties really well into event-driven architecture, although it's gotten a lot more notice since with the rise of microservices architectures as well, because it also dovetails nicely with that. Von Vernon has written Implementing Domain-Driven Design and then Domain-Driven Design Distilled, which is probably better known than the Implementing book. All of these are really great sources to learn about this kind of practice. Highly recommend Eric Evans in particular. Now, there's a number of key concepts. We're going to focus on a couple of these, but these are all things that you learn about reading through the book. Ubiquitous language and bounded context are the two that I really want to focus on. We've already talked about domain events, and it's not a coincidence that domain events are a key part of domain-driven design. Now, bounded contexts help you to segment your application into logical areas. For instance, right now we're looking at the cafe context of this business. Obviously, there's a back office, right? Because coffee shops have lots of different locations, each one of which is a cafe. The customer loyalty system is different, right? You're going to talk to marketing people when you're building the customer loyalty system out. Inventory is going to deal with supply chain stuff, right? So these are all sort of different spaces that have different business owners. And part of the idea behind domain-driven design is that we focus on the domain that we're solving for, in the moment. Right now, we're solving for the cafe itself, not the greater corporation or the greater system. So we're not going to worry about those other concerns, and we're not going to produce one big, say, monolithic application where all of this would blend together, right? We're going to build out just the area that we are concerned about. The other piece that's really key here is ubiquitous language. And the ubiquitous language means a set of terminology that's agreed upon between the developers and the business owners. So for instance, as a programmer, if we were designing a system, we might have said things like order placed and order ready. But in a restaurant, that's not the terminology that you use. We use the terminology order in and order up. Another good example is if we were out of something, we might say item expired or item out of stock. But in restaurant terminology, you say item 86th. So by using a ubiquitous language, we work in the same language that our business owners use, and it allows our domain experts, our business owners, to be better participants inside the system and allows us to build better software and doesn't breaks down the sort of lack of understanding of that problem space. And the ubiquitous language is also something that you need to continuously refine and take care of. It's really a top-level concern. In our application, it's modeled as its own, not a microservice, it's a jar, because it's just a domain jar, but all of the services have it as a hard dependency. A lot of times we talk about in microservices architectures that we don't want cross dependencies. I think in this case it makes sense because the ubiquitous language is of primary importance when implementing domain-driven design. So I think it makes a lot of sense to have that as a dependency across microservices. Some other things that we're going to look at: aggregates, entities, value objects. These are just ways that we design our system, and we will look at those as we jump over to IntelliJ and look at some of the code inside of this system. Okay, so let's do a little bit of a code review. So one of the concepts we talked about was the ubiquitous language, and in our application, this is captured inside of the domain project. And the domain, one of the points of wisdom about microservices is that you shouldn't have dependencies that go across microservices. Well, this domain is a dependency that goes across all of our microservices. We have two, domain and test utilities. The test utilities is, of course, optional, so a microservice doesn't have to use those if they don't want to. The domain, though, in my opinion, it's justified by the importance of the ubiquitous language or the domain language inside of domain-driven design. I think it's very important that we be on the same page with what these are called. And let's just look at what a few of these objects look like, right? Where events are how our systems talk to one another. So we don't send specific, remote method calls across services. We don't make REST calls. We're putting events on top of Kafka topics. So an order up event is how we know that something is ready, right? An order in event is how we know that something is in, right? We have an event type. In our event, these are the types that we have agreed upon, right? Beverage order in, beverage order up, kitchen order in. 86 is when we're out of something. We also have other things like an 86 exception, right? So an 86 exception is thrown by an application, although what it really has is a collection of 86 events, and the application will then put the 86 events back onto the topic, right? So it's really the event that we use to communicate, not like throwing an exception, right? So, and we'll look at the barista or the kitchen, for instance. Whenever the barista makes a beverage, it has a copy of its local inventory, running in the application. If it violates that inventory, it will throw 86 events, right? And the event is the rest of the system then reacts to that event and says, okay, we need to either restock or we need to not take orders for cappuccinos for a while. So that's part of how our domain works. The next piece is the core object. It's the core service. So the core is the service that handles all the routing. And the entry point to the core service is the Kafka service. In the service, we're following domain-driven design kind of patterns for how we name these things. It orchestrates what happens. It's got a handle on an order repository. We're going to persist order objects. We'll talk about Hibernate Panache a little bit later. But an order repository gives you access to a lot of methods by doing nothing more than that. If you've used like the Spring stuff, it's pretty similar to that. In these channels we have here, we are injecting emitters, which are how we're going to send something out to Kafka. We also have an incoming listener that's going to get messages coming in from the website, and then we're going to handle a create order command. And we use a command object, and that is again part of the convention of domain-driven design. We have an order in command, and that command contains an ID for our order, a list of beverages, and a list of kitchen orders. And what we do with that is we call a static method on our order object. This is an aggregate in DDD parlance, and it has a method called process create order command, and that gives us an order created event. This event is just a value object, meaning something that the system doesn't really care about, but we're going to use it for a little period of time here. And what we're going to do is that order created event is going to have a reference to the actual order that we've created. It'll pass that to the order repository to persist it. And then it has a number of different of beverages and or kitchen orders, which then get looped through and sent asynchronously to Kafka. So when we pull in, we ordered a couple of coffees. So when we order those coffees, those will get sent on a topic and picked up by the barista object. Now the barista has its own Kafka service, and it's going to look, it's a little bit simpler, right? It's not doing quite as much. It has an order up emitter that it sends orders out to, but it handles an order in, and it just calls the barista object's make method. And what this is going to do, as I mentioned, our barista has this is how we get the name, right? So we're using the name of the pod to say to use as the barista's name. We have a copy of an inventory object that just has the amount of materials needed to make our beverages. But make just applies a different amount of time delay based on what you've ordered. So we've modeled out that a cappuccino takes longer than a black coffee. But our method here, we are going to adjust our inventory and look for an exception in case we have run out of something. If we've run out of something, what we're going to return is going to be 86 events instead of our beverage up event. If we don't do that, then we just create a new order up event. And our order up event will then be put back on the Kafka topic, picked up by core. It will realize that the beverage is ready, and then we will notify the website, the web front end. And there's one other piece that's that I want to show you inside the web front end, because it's a nice Quarkus feature. This is our dashboard resource. So this is what the web page is talking to when you see the dashboard that updates the status for the drinks. And what we're doing is we're listening to Kafka here, and this publisher is then returned to the web page at this URL, and anything that comes into Kafka is just automatically streamed over server sent events to the front of the web page. And so that's how it gets all of the updates from that's where it gets all of the updates from Kafka. All right, so the updates to the website are streamed directly into a Kafka topic, where they're picked up by this class and then sent over the wire to the web page. And so that is the end of our very quick code review. All right, so how do we build out our Kafka architecture? Now, Kafka is extremely fast and extremely scalable, and it's very easy and often very tempting to have lots and lots of Kafka topics all over the place. And in many cases, that's not necessarily a bad architecture, but it's not what we're going to recommend for an event-driven system for two reasons. Now, the first is Kafka can guarantee ordering, but only within one topic. So it makes sense to group like events within a single topic, meaning whatever happens inside of our orders makes sense to go inside of an orders topic. It makes it easier for us to guarantee that those come in order, and for us to go back, pull those out, and make use of those to replay those events or to recreate system state. So we might have a web topic, for instance, and that will detail everything coming in and out and going out to the web. We could also have another topic called orders, and that would be everything coming in and out of orders. Our inventory system would have its own topic. So you don't want to be too parsimonious. You don't want to jam unnecessary things together. But like say all of your orders events, if they're all logically grouped together around an order, they kind of belong in the same topic. Anything around your website belongs in the same topic, right? Or inventory system, or other whatever your design might be. There's another reason for that, and that Kafka is extremely performant and extremely scalable to the extent that you will run into bottlenecks that come in around what are called partitions. And each topic, like in this case, your orders topic, will have multiple partitions. Producers talk to a partition and consumers read from a partition. So to the extent that a bottleneck exists inside of Kafka, and by that term, Kafka, I don't mean to downplay the performance levels of Kafka, But to the extent that a bottleneck exists, it's going to exist at the partition level. And it's going to be the more topics you have, the more partitions you have. When you make changes, it becomes tougher to make changes. So that would be the one place that you can run into a problem. So there is a technical reason inside of Kafka to also somewhat try to limit that. Don't be overly concerned with that. Kafka is incredibly performant. And can handle a massive amount of messages. The real reason for this is just the logical partitioning, or being able to group your events together logically, is the real advantage of designing your Kafka system this way. Now, how do you design and deploy on Openshift? So Tosin, I will let you take over here.
So the way we decided to design and deploy the Quarkus Cafe on Openshift in our application is we decided to use 3 different technologies. We decided to use operators, Helm, and Ansible. So we'll start with Helm. With Helm is used to manage the 5 different microservice applications that make up the Quarkus application. And the reason we'd use Helm is because those 5 different applications could have 5 different versions. And what Helm allows us to do is manage the versions in one instance of the deployment. So for an example would be a Helm 1.0 version could be a version that contains multiple 2.4 versions of that microservice, or 2.3 in that same version. We decided to use Ansible to deploy the infrastructure for the application. So with Ansible, what we did is we used Ansible to deploy the operator, and the operator deploys Kafka. So once Ansible deployed Kafka and using the operator, Ansible then deployed MongoDB. As we go to the next slide, I'll dig into where all these things go and plug together. I'd like to now discuss how the application is constructed using operators and Helm charts. So as you see in this diagram, we have these two are separated in 2 different boxes. The first set is the Kafka cluster, and that consists of the Kafka instances, the Zookeeper instances, and the operator that deploys the Kafka instances. So let's go and look at how that operator is constructed. When we go to the Administrator tab, and under Operators and Installed Operators, you'll see the Red Hat integration AMQ streams. This operator consists of different APIs that will manipulate the environment and configure the Kafka instances for you. In this example, we're going to be using Kafka and the Kafka topics. So let's dig down in the Kafka. Within Kafka, we have a deployment called Kafka cluster, and within those deployments, you'll see different resources defined. Those resources consist of the stateful sets for the Kafka instances, the Bootstrap stateful sets, the Kafka Zookeeper instances that are used to manage the Kafka instances, and other things such as the deployment controller for the operator and the secrets that are associated with each of these deployments. If we go into workloads, we'll see the different pods that's made up of the Kafka cluster and the Zookeeper cluster. I talked about earlier about the Ansible playbook that deploys this. So within the Ansible playbook will deploy the Kafka operator, and then it will configure the Kafka operator to deploy the 6 instances that you see. The Ansible playbook would also deploy this MongoDB instance that we're using within the Kafka cluster and within our Quarkus Cafe deployment. Now let's look a little more into the Quarkus Cafe. Quarkus Cafe is made up of 5 different microservices, like we said before. And you see here below, there's a Helm chart. So this Helm chart is what's used to manage the different Kafka instances, the different Quarkus Cafe instances. So let's look at that. So if I click on Helm here, you see the Quarkus Cafe deployment. Under the Quarkus Cafe deployment, we can click on resources. These resources define the different deployments and the services that go with the deployment. You'll also see the service account. This service account is needed to deploy all the instances within the Kafka cluster, within the Quarkus Cafe deployment. Let's click on Barista, and we see under Barista in the YAML file that we have a tag labeled here for the Quarkus Helm chart That 1.0 version of the Helm chart is referring to the collection that we defined before of all the versions of the different microservices. So for the Quarkus Cafe Barista app, for example, that is on a 2.4.0 version, and we made sure that all these tags would be linked to this 1.0 version. So when we do another update to 1.01, we most of the time this might change. It might change on the barista, or it could change on the core, and it could change on another piece of the deployment. So that's where Helm comes into play. And as you can see here, you can see the revision history. If we wanted to deploy a different version or an updated version of the Kafka, Quarkus Cafe Helm chart, you would see there would be another revision 2, and it'll show the date that was updated and then the date that we deployed it. It'll also show the chart version and the application version. So that is it for the high-level overview of how we constructed the Quarkus Cafe app with Kafka operators. Thank you.
Thank you very much for attending our talk. You can find both of us on Twitter. We'll also share our official Red Hat emails. We're both on LinkedIn, and we will be around for chat for questions and answer for the next 15 or so minutes.